Hi everyone, this topic is going to be looking at sound waves, and we will talk about earthquake waves as well near the end. But to start with, what is a sound wave? What type of category does it belong to? It is a longitudinal wave. So sound waves are longitudinal waves. That means it has areas of compression and areas of rarefaction. So if we consider in this diagram A, that's the air undisturbed with no oscillations passing through it, then that's how we can imagine sound, well, nothing actually, not even sound waves, just the air being in front of us, the air particles being in front of us. Now, if I do start talking, then there will be vibrations, which we call the sound waves, which cause areas that are less dense, which we call rarefunctions, and areas of compression. This is something that we have seen in video 1. If you don't remember it, please go back to it. And then you can see that there's another area, rarefunction, another compression, rarefunction, and so on. So as the wave travels through, the energy travels through the air, you expect to see areas with this high compression and areas of low compression. And then you can see in C is how we simply can draw it in a graph of distance, displacement against distance. And you can see from these that the areas that are highly compressed, so the compression areas, are always represented with the amplitude, whereas with the highest amplitude, somewhere in the middle, you can see the point is at the beginning of it, and then the compression is like a negative part of the graph. You can also label between this middle point of the rarefunction and this middle point of the other rarefunction gives you a complete wavelength. That's just a quick reminder again of the previous topic. So this is one wavelength, 2, this is one wavelength, and so on. So this is just a quick recap of what we've seen about sound waves. Before I continue into the learning objectives and expectations from the course, this is a device called an oscilloscope. Now, what we use an oscilloscope for is to view the waves through an electrical signal. So if I connected, for example, a microphone to this and I started singing through it or making a specific noise, then the oscilloscope will show me the wave created. So here there's 2, so they're probably connected to 2 different microphones in this case, or something like that. And you have 2 separate waves that are being drawn onto a screen. So basically, an oscilloscope is used to show vibrations on a screen, but it doesn't tell you much about the axis. So in other words, because it doesn't have an actual axis that we're used to, in other words, what you have is the voltage signal, which in other words is our amplitude. And I will explain how to work it out. And it's worked against time. So you can also, there's a lot of dials on the oscilloscope that you can change it to microseconds, milliseconds, seconds, and so on, just so that you can make sure you can see clearly the wave and read through it. So it's a good device to analyze waves. So why do we even care about this? Well, you will have exam questions based on this, and I'll show you some exam questions in a bit. But the idea is that for this particular reason, we need to analyze how sound amplitude and sound frequency affect certain features of sound. So let's start by imagining that I'm making a nice constant sound, and then all of a sudden I decide to increase the loudness of the sound. So what I will have to begin with is my wave looking like this. But then if I increase that sound, what I will experience is something like this. So what you can see, if we assume that this is the rested position, what we can see is that our amplitude here is lower than the amplitude here. So loudness affects the amplitude. So directly, every time you're asked regarding how loudness affects a wave, it actually affects the amplitude. And the amplitude also kind of tells you about the energy that the wave carries. So the louder the sound, the more energy the sound waves will carry, and hence the highest amplitude. Another feature that you're aware of is the frequency. So we usually get the frequency. So if this was these both are displacement time graphs. Not displacement distance graph. If you forgot about this, please go back and look at the previous videos. So the second point that you could also investigate, since it's a displacement time graph, we already know that frequency is how many waves pass a point per second, and is inversely proportional to the period of a wave. From a displacement time graph, you can get the period of a wave from one point to the adjacent same point on the same wave. So that will give you the period. And if you notice that, for example, you increase the pitch of the sound, so pitch is another feature, then what you will expect to have, let's say going from this loudness, remaining in this loudness, you will expect to see your wave being closer together. So you will have a shorter time period, but since you have a shorter time period, then that means your frequency increases at the same rate. So that means higher frequency is higher pitch. So just to quickly summarize, because you will need to be able to answer questions like this, and I'll do some questions as well. It says in this point, to describe how amplitude and frequency of sound waves are linked to loudness and pitch. Just to quickly summarize, amplitude is linked to loudness and frequency is linked to pitch. Like we said already, the louder the sound, the bigger the amplitude. And you can imagine water waves like that. So if you have, for example, a water wave like this, it will have less energy than much higher water waves. So the higher the amplitude, the louder the sound. And for the higher the frequency, the higher the pitch of the sound. So the next part you do need to know, I don't know if you also noticed that these targets are not, there's no targets included for grades 1 to 4 because it's considered as a higher tier paper. So what we have is the second point where it says state the range of human hearing. Frequency. If you don't remember this already from your year 7 or 8, human range hearing is 20 hertz to 20,000 hertz. Now, some of you will have you'll be able to hear sounds with less than 20 hertz frequency for sure. None of you will be able to hear anything above 20,000 hertz. Some animals can, and that's how they navigate through life. But for humans, we can only hear between sounds that have a frequency of 20 hertz up to 20,000 hertz. And as you get older, then the less you can hear from the higher range as well. So you probably won't even be able to hear sounds of 20,000 hertz to begin with. But as you age and as you use your headphones a lot and all of these things that you use with loud sounds, it will lead to your hearing to drop from 20,000 hertz to even lower and lower and lower as you grow older. So the third part of target grades 5 to 7 is to use an oscilloscope trace to state the frequency of a wave. And this is very important. Remember, there's two different graphs. displacement distance and displacement time graph. An oscilloscope only shows you the displacement time graph. So, since we know that this axis here is time, and we know that frequency is inversely proportional to time period, then we get the period of one wave. So from this point to this point, for example, we get the period from here. So how long it took one wave to complete an oscillation. Then we do frequency is equal to 1 over that period. So that should be straightforward if you got that from the first few videos that I shared. Now the next part of this video is to describe how the human ear structure allows for sound detection. Now there's some parts of our ear, we consider this to be the outer part of the ear, the middle part, and we have the inner part. Now the pinna, the part of the outer ear, its sole purpose is outside of that ear. Obviously we can all touch it, and it is to collect and guide sound waves to our ear canal. So what we have is a lot of sound waves arriving to the ear, and it collects and sends them through the ear canal. Now this is again the air particles vibrating, and those air particles will reach the eardrum. Now as the air particles enter the ear canal and continue to vibrate back and forth, they will reach this very thin membrane. This is the ear canal, remember? They will reach this very, very thin membrane called the eardrum. And as they're pushing back and forth, so will the eardrum push back and forth. So it will start oscillating. A very good comparison to the eardrum is either a just normal drum actually. So if you get a normal drum and you hit the surface with a drumstick, then the surface will start vibrating just because of the hit. But obviously the eardrum is much more sensitive to any vibration, and it vibrates very easily. Now, so far we looked at the outer part, which ends at the eardrum. Now let's look at the middle part. So I made a bit of a wrong thing in here. Now, the middle part consists of the three smallest little bones in a human body: the hammer, anvil, and stirrup. Now, we call all of these things, all of these bones together, we call them the ossicles. So, we said already, the pinna collects the sound, guides it through the ear canal, which causes the eardrum to vibrate. This is the outer ear. Now in the middle ear we have the ossicles. As the eardrum is vibrating, it's actually connected to these little tiny bones we call ossicles, and they start vibrating. So what the purpose of these ossicles is to transfer vibration or vibrations to the inner ear. Now you say, why do we need those little bones to do that, to transfer the vibration when we have an eardrum? Well, they actually do something a bit more. Ossicles actually amplify the vibrations. And that is necessary because in the cochlea, this very weird looking, snail looking shape that we have here is filled with liquid. So since the cochlea is full of liquid and we want to pass the vibrations from the ossicles to the cochlea, they need to be amplified. The pressure needs to be stronger, and you experience that every day from, let's say if you wanted to run in air, which you do, you can do it much easily than you would be able to run at the same speed in water. So you have to increase the pressure against it. So we spoke about how the ossicles transfer the vibrations to the inner ear, so that's part of the middle ear. Now this, from this point onwards, we'll look at only the inner ear. This is called the cochlea. It's got these three semicircular bones, and that's just to maintain your balance. It actually helps us maintain our balance. So now what we have is that we have the ossicles vibrating, so the sound wave, in other words, from entering the ear, sound waves turned into vibrations from the solids, and then those vibrations are passed on from the ossicles to the cochlea. We're not interested in these three because they only help us balance. It's not involved in sound. But this part of the ear, the cochlea, is full of liquid, so these vibrations pass through the liquid and get converted into electrical signals. Now we're going to focus a little bit on what actually happens here. Just wanted to remind you a little bit quickly that when you have sound waves in air, they travel slower, so air speed is lower than in a solid speed, which is higher. Now when a sound wave passes from air, let's say, to a liquid, even though it speeds up, so we know that V is equal to F times lambda, frequency times wavelength, the only thing that remains the same at all times is the frequency. It's a very key part of what we will talk about in terms of what happens in the cochlea. But the wavelength, so if the speed increases, wavelength will increase with the frequency remaining the same at all times. So what we have is in the cochlea is this liquid, and then these are really tiny little hairs. They're hair cells, but for this simplicity of it, we'll call it hair cells. So you'll have different lengths of hair cells, and these vibrate at different frequencies. Now, the reason that we can only hear between 20 to 20,000 hertz, so that's the human hearing range, okay? Not every animal, other animals have different hearing ranges. Now, the fact that we have that specific hearing range is due to the fact that these individual little hairs vibrate at different frequencies. I'll also include another part here. So if I had a pendulum, so I hanged something from the ceiling, a ball, let's say I hanged a string from the ceiling, so this is the ceiling, this is my string, and this is the ball I hanged on it. Now if I push this and I let it freely oscillate, start going this way, then the back, and so on. And it will vibrate at its own will. I know I disturbed it to begin with, but it will be vibrating. So if I sat there and counted how many back and forth it completed in 1 second, then I will know the frequency of the oscillation. That's called the natural frequency. So when you push something and let it vibrate at its own natural frequency, you can measure it, and then you will notice that if you force vibrate this to that frequency, so if I actually hold it now with my hand and force to and vibrate it at that frequency myself, then what will happen is that this ball will go to higher amplitude vibrations. That's how some buildings come crashing down when there's an earthquake, but I'll get to that in another time. This is quite similar actually to what happens with our those little hair cells in our cochlea. Vibrations that match the vibrations that we can hear tend to cause the hair cells inside the cochlea to vibrate, and hence we pick those sounds better. So those sounds have frequencies from 20 to 20,000 hertz. Now these little hair cells are also called nerve cells. They pick up the vibrations and they send it to a special place down the auditory nerve, basically. So all these vibrations are turned into signals which are transmitted through the auditory nerve to the brain where we hear sound. This happens very, very quickly. So far we have spoken about the amplitude, how it's linked to that, stated what the human hearing range is, talked about the oscilloscope trace. We described how the human ear allows us to detect sound and why humans can only hear a range of frequencies. Now, to explain the difference between general noise and music goes back a bit to the beginning. In general, when we hear a specific type of music that we like, it's because they have a very specific rhythm. And the sound waves do tend to change smoothly. The wave pattern in general repeats. So for example, let me go back to this part. So for example, music can involve a range of different frequencies and a pattern that constantly repeats. So let's say this is the pattern that constantly repeats with sound waves. When it comes to general noise, now the general noise is made up of sound waves that constantly vary in frequency and have no pattern. So if you hear something noisy and it's giving you a headache, it's because your brain cannot pick out all of the different frequencies that are taking place. So, for example, you might have something like this mixed with something like this, mixed with something like, and so on. So it will be very, very complicated. It will be really hard to figure out the pattern. So just for a heads up, musical notes are easy to listen to because you have wave patterns that repeat regularly, whereas general noise is made up of sound waves that vary in frequency and with no clear pattern. The next part of this video is about ultrasound. So what I will start with is to state what ultrasound is and compare that to human hearing range. Now, ultrasounds are simply sound waves. So ultrasound are sound waves above the highest frequency humans can hear. So they're basically sound waves above 20,000 hertz or 20 kilohertz, which is the same exact thing. Now, since they're already sound waves, we also know that ultrasound should be longitudinal waves. Most of you know ultrasounds as a way of scanning in a woman's womb for a baby, but they're also used for a lot of other treatment, diagnosis as well. So you can look at the kidneys or any damaged ligaments and muscles, and other ways of also helping is that ultrasounds can break down big stones in the kidneys into smaller ones. Now let's start analyzing the basic of an ultrasound scanner. So you have a transducer. So this is the device that's on the lady's belly. This is called a transducer. The transducer produces and detects cells or pulses of ultrasound wave. So the transducer, once again, detects and produces ultrasound waves. So it's one device in two, in other words. So we send out sound waves through it, and it also receives it. And then you also have the control system, which analyzes these very, very quick signals and displays it on a screen, as you can see here. Now let's imagine we're having pregnant ladies having an ultrasound, and exactly what happens. So we have the transducer, which is connected to a control system and then a screen display. Now, when each ultrasound wave pulse that comes from the transducer is actually partially reflected at each different tissue boundary in its path. So you see it's coming out like this. Now, at this part of the tissue, some of it will be partially reflected, so it will be reflected back. Some of it will still transmit through it, though. Now, the part that reflects back at each different layer, so you have a layer here, you have another layer here, you have a layer here, and so on, all the other parts. So each time a sound wave, an ultrasound approaches a different tissue boundary, it gets reflected and hence returns back to the transducer, which picks it up. And since at each different layer is a different distance, it takes different time for it to return back. So every ultrasound that reflects at each different tissue boundary, it arrives back at different times. And since the transducer is moved across the body, then all of the ultrasound waves that are detected by the transducer are used to build up an image of what is going on inside the body, of the internal tissues of the body. And that's what you can see here. That's why you can see these different tissue boundaries, including the baby within the belly. So far we have spoken about what ultrasound is, how it compares to the human hearing range. Obviously, it's any sound waves that are above 20,000 hertz. And we also talked about how an ultrasound transducer operates using partial reflection. Now I'm going to go into the explaining why ultrasounds are safer than X-rays. So why doesn't a pregnant woman, why is a pregnant woman not allowed to have an X-ray and she should be having an ultrasound instead? So the first reason is what we have already discussed. It's the fact that ultrasounds can reflect at boundaries between different tissue. So you can see organs and other soft tissues in the body, which X-rays actually cannot do. You cannot see the organs in an X-ray because it picks up only the bone structure mostly. And the second reason is because they're non-ionizing. So ultrasound does not have enough energy to remove electrons from the atoms or molecules that make up our DNA, which means that it's harmless when you use it for scanning. So it's non-ionizing radiation, whereas X-rays are ionizing. They have enough energy to knock out electrons of your DNA structure and cause tumors to form. Ultrasounds don't only have a specific use for humans, they also have a very good use in industrial imaging. So any flaws in metals or anything that you can't really see unless you cut open the metal, so it could be a crack or anything inside the metal, then you can detect it using ultrasounds. So in this example, you see this is the metal that we have here, so the metal plate. Then this is a crack or a discontinuity in that metal. And that's important, especially in a lot of our devices that we use. There shouldn't be things like that. And that can cause a real issue over the long term. And this can happen from years of damage or in any other way. And one of the uses actually I've seen when I went to this physics speech, they were talking about wind turbines. So wind turbines are quite massive, and when they're built, they're expensive to carry on and so on. The lady that worked on the wind turbines, I know that doesn't look like a wind turbine, but imagine it does look like one. the lady said that if there is a fault within any of the blades that turn for the turbine, it could cause an overall bad response and it could be dangerous as well. So the lady discovered a device that she could place inside to identify those faults. Now, it's very serious if things go wrong. It could destroy money, could get wasted. So instead, what people started using ultrasounds. This is not exactly what she used in this case, but it was an example for you to see what I mean in terms of why it's important to know if there are cracks in any of the devices we use. So what you see here is an oscilloscope reading in a way. So what you have is your transducer. This is supposed to be the transducer. And the first wave that gets reflected is from the surface of the metal. So you can see the initial pulse is high. So what you have is waves going in, but also getting reflected and picked up straight away. Then you have, partial reflection, not fully reflected. The rest of the wave continues in. And once it meets the different boundary, because that's a crack, it's obviously going to have a different density, hence it's a boundary, and partially some of it gets reflected back. Now what gets picked up here is this crack echo. So is there a reflection that comes due to the partial reflection that comes due to that crack being in place. Now some of it will still keep going on, getting transmitted, and once it reaches the end point of the plate, it gets reflected back to the transducer and gets picked up as the back surface of the echo. So what we have in simple terms is a constant transmission, so wave traveling, and partial reflections at different boundaries. So the fact that it did pick up the initial pulse, so the beginning and the end, if there was no crack echo or any other signal picked up, that means that the plate is fine. But since there's a crack echo, it means that there is a point there that needs to be investigated. We can actually use this to calculate the position of a flaw in the metal. Once again, the difference is how long it takes for them to travel from one point to the other. And if you know the time and you know the speed, so if you have the time is known, which can be found from the actual oscilloscope readings. So when you know the time it takes for it to go to the crack and return, because that's what we are actually getting from it. And also, if you know the speed of ultrasound in that specific material, then you can calculate the distance with the simple equation that we all know and love. Distance is equal to speed times time. And since we already said that the time is the time it takes for the wave to go to that point and come back, then we know that we have to use half of the speed times distance, speed times time. Otherwise, it will give us double the distance. So here we kind of covered how to describe how to use the ultrasound distance measurements, how to use ultrasound traces to calculate position of a flaw in a metal, and how to collect the time between ultrasound pulses. Well, the time always gets taken by the peak to peak distance, since it's a time base. It's always time base. So then that's the time it takes from one pulse to the other. So in this first statement of the specification, it actually states what we've talked about, how ultrasounds can be used in terms of, how they get partially reflected, or even sound waves that get transmitted through different materials. How can they be used for detection and exploration of structures which are hidden from direct observation. So we spoke about ultrasound use in that way. We also spoke about exactly what ultrasounds are. Like this statement exactly summarizes what we spoke about all this time for ultrasounds. So the key points to take from this is what it is. So it's above 2000 hertz. And that when we use them, they get partially reflected at different boundaries. And what we use is the time taken for the reflections to determine how far each thing is, and the equation that we can use. So we can use them both for medical and industrial imaging. There's another bit that I want to go through before I proceed to talk about seismic waves. Now, echo sounding is another thing that we tend to use a lot to figure out distances to objects that are underwater usually. This is quite similar to what works with ultrasounds. So what you have is a transducer. So at the bottom of the ship, you have a transducer that emits a pulse of ultrasounds. Once again, we're using ultrasounds here. That pulse reaches the ground. Once it hits the object, so the floor, the bed floor, it reflects back to the transducer where it detects it. And what it does, it actually times how long it takes the pulse to go from the object and back, and then use it to calculate the distance. So it times how long to go and return back. And since it already knows the speed of the ultrasound, so that's already a known again, just like we know the speeds of ultrasound in different tissues of the body. And you can use distance is equal to speed times time to calculate the distance. But once again, we're talking about how long it takes to go down and come back again. But I only want to know the distance from here to there. So I need to half the distance once I calculate it, or I can do it from the beginning and half the time. So that will be a half times speed times time. So very similar to what we looked and analyzed in terms of ultrasound being used inside the body or industrial uses. The last bit left is the seismic waves. For those of you who are interested in earthquakes, the study of earthquakes is actually called seismology. And people who tend to study seismic waves do gather a lot of information about the structure of the earth. There's a point here on the specification that says students should be aware that the study of seismic wave provides new evidence that led to the discoveries about parts of the earth which are not directly observable. So this is not just a topic about seismic waves, but it's also got to do with the structure of the earth. Obviously, we cannot drill to the center of the earth. It's impossible. It's too hot. And we can barely reach the surface of the earth, actually, in terms of drilling into it. So the other way of discovering how the structure of the earth is to analyze what takes place within the earth. And the only way to do that is through the waves, and I will explain that. Before I move on, just let's get a good look at the structure of the earth, which you should know. So you have the crust at the beginning. So the top layer that we are all currently on is called the crust. It's a solid layer that's about 50 kilometers thick. And this is where the earthquakes take place. Now, obviously, the crust is 50 kilometers big. And usually the earthquakes start because of a build-up pressure between different plates. I'm not going to go into it now because it's more of a geography topic. With the tectonic plates pressuring one under the other and so on. But you should know a few key things. So the point where earthquake begins is called the focus. So it doesn't matter which point it is at in those 50 kilometers. We call that the focus. So this is the nearest, this is the point where the actual earthquake originates. And then the nearest point on the surface to the focus, we call it the epicenter of the earthquake. So let's say it will be here, directly above it. That is called the epicenter of the earthquake. Now, earthquakes are usually recorded by detectors on the surface of the earth. We call these seismometers. So they are detectors. There are loads and loads of detectors all around the earth, and they usually share information from country to country and communicate in terms of what results or what waves they received and so on. So the whole purpose of seismometers and their results being shared across the globe is very important, and it has been a very important part of how the structure of the earth is, discovering the structure of the earth. So before I continue, let's just do a quick check on the learning objectives. So the first one is to describe the internal structure of the earth, which we have done. And we're going to move on to this part now. The idea is that you should know the internal structure of the earth, and then we're going to link it to how seismic waves actually explain how we decided that the structure of the internal structure of the earth is the way it is. So let's move on to a seismometer. A seismogram. A seismogram is what you get when there is an earthquake. Now, when you look at the picture here, the first thing you see is the P wave. So P waves are also known as primary waves. They last about a minute and they're longitudinal waves. So what you expect is that as the longitudinal waves travel through the material, it pushes and pulls on the material as it moves through the earth. And the second part that you can see is the S wave. Now, if you notice here, there's a big bracket that says body waves. You don't need to know these names, so it's not necessary to know it. It's just that the P wave and S wave are the main important waves that you do need to know. So S waves are also known as secondary waves, and that's because they arrive after so they arrive a few minutes later from P waves. They are transverse waves, so they're different to the P waves, and they actually move more slowly than P waves, which is expected as the internal structure, as even the solid structure that they can travel to is denser for longitudinal waves, remember, so the longitudinal waves travel faster through denser material. And what they tend to do, secondary waves tend to shake the material that they pass through inside the earth from side to side. So what you have after secondary waves is what we call the L waves. They only take place in the Earth's crust. They actually arrive they travel more slowly, and they arrive after P waves and S waves. So this is a seismogram, we said. Now it looks quite beautiful as a seismogram. You will expect to see it in a normal, just plain, simple image only. So what you have at the bottom is the time axis. So this could be at time 0, for example, so that would be 0 minutes, and that could probably be after, 10 minutes. So what you see is the P waves arriving first, which are longitudinal, so P primary waves. Secondary waves arriving second, so the secondary waves, and the L waves that arrive later. For our course, we're going to focus on the primary and secondary waves. The L waves are not a necessity to know so far. So now this is the point where we're going to explain how the waves passing through the Earth led to the discovery of its internal structure. So as I said already, there's when an earthquake takes place, there's seismometer readings from different parts of the world, and they use them to find where the epicenter is, so the place where, on top of the focus where the earthquake took place. Now, P waves and S waves bend as they travel. So in this case, the S wave is the red line. So S wave is the red line that you can see here on the graph. And P waves are the blue lines that you can see. And I will explain what happens. So we already said that this is the crust. This is the mantle, which is a semi-solid structure. Then you have the outer core, and you have the inner core. Why am I mentioning this again? Well, we're going to come to it in a second. And you can see from the diagram that S waves are bending and moving in different directions. Now, they actually bend because as they are traveling through the mantle, their speed changes gradually with the depth. So the direction also changes. This goes back to the last part 2 video, the last video I've done on this. So part 2 of P12, where we talked about how waves change direction and speed as they go from a different density material to a different density. So the reason that they bend is because the speed changes with depth. So you can see that both the S wave and the P waves bend in different directions. But you can also see that the S waves do not pass through the outer core. Now, S waves are the secondary waves, and we said they are transverse waves. So transverse waves actually cannot travel through liquid. Hence why the S waves are not found in this region. And from this, we know that the outer core is actually made of a liquid. It's a liquid part of the Earth. But at the same time, you can also see that the P waves, which are represented by these blue lines, as they are bending slightly because of the change in density, as soon as they reach the boundary between the mantle and the outer core, you can see a bend into the wave, the P waves, the longitudinal waves. And that happens because even though P waves can travel through solid liquids and gases very well, but they can't travel through vacuum, so that's the important part. But you can see that they actually refract at these points. So P wave is coming in, it refracts between the Earth's layers. So you have semi-solid structure here and then liquid structure here. So it abruptly refracts, it changes direction because the speed changes. And then as it exits again, the outer core in this region, it bends again because of the change in speed. So now we know that due to these bends here, there's a different material, and the fact that S waves cannot travel through this is a liquid region, so the outer core is liquid. And we can also see that if there's a point picked on the opposite side of the epicenter, it travels straight, because when it travels straight on, direction doesn't change. And hence we know that P waves also travel through the inner core, whereas S waves cannot get to the inner core. And the last point I wanted to talk about here is the shadow zone. So you have a S wave shadow zone, which is basically pointing out the fact that no S waves have been recorded at all in this area, actually in this whole area. So from 103 to 130 this direction. So the reddish orangey color. That's called the S shadow zone, because waves cannot travel through the outer core as they're transverse, so they can't travel through a liquid. and that's been shown by a lot of seismometers not receiving any readings for S waves in this direction, but this area probably did receive from the epicenter, but not this area. Now P waves also have some shadow zones. So you can see in this case, in this example, they are here, but some P waves are recorded here by different seismometers around the world. Now, when P waves get refracted at the boundary between the mantle and the outer core, it causes a second refraction as further around, and that means that the waves cannot reach the shadow zones. Now, this is another reason why, this is another proof of the fact that the outer core is liquid, because it helps P waves refract quite significantly when it exits and enters. And that's why we have P wave shadow zones. Now, the last point to make, the third point to prove that the structure of the Earth, is the fact that when they discovered the boundary between the crust and the mantle, and they found that it was about 50 kilometers under the surface of the Earth, it was discovered by them calculating the speed of seismic waves at those different at those different depths.